working. So first I would like to thank Mark and the organizing committee for this amazing opportunity to present our technology in this important conference. And I will focus in my talk on the shift that we want to see in the industry from cell processing to tissue processing. And I will introduce in this talk the technology that we developed at Ever After Foods that allow to produce macro tissues at scale. And this technology is currently available for all the cultivated meat industry and also for food players. So briefly about the company, we are located in north of Israel. Recently we secured a strategic investment from strategic partners, Cargill and Buller. And our business model is focused on a B2B player technology enabling platform. I would like to start with discussing what we, and personally me, see as the main bottleneck of the industry. And this is basically by the fact that we take animal cells that naturally grow in solid phase under very low and controlled shear stress and force them to grow in this stir tank that generates very high shear stress. And the two main drivers that increase this shear stress is increasing cell density and increasing the scale. Well, unfortunately, those two drivers are the main drivers to reduce the cost also. And this is why many companies and many players starting to basically selecting the cells, manipulating the cells to adapt them to these extreme conditions. And some of them do it using genetically engineering or even spontaneous engineering of the cells. But they're losing their natural to create tissues. So they all compromise with this cell soup, this cell slurry, which is far away from meat. And more than that, if we compare to the CHO cells, which is the most investigated cell line in the industry, most of them are hardly achieving even the productivity of 2 to 5% out of a 1,000 liter bioreactor. So in our company, we decided to take totally different direction. Instead of manipulating and adapting the cells to the stir tank technology, we decided to design a technology that will be suitable for the natural needs of natural cells. And we call it the edible packed bed technology. It's based on fixed bed bioreactor that allow us to grow macro tissues at large scales. So briefly about our technology, we use totally different bioreactor. We basically work in columns bioreactor in fixed bed configuration. We put the scaffolds, as you see here, inside columns. We can put multiple columns in that, and we totally separate the reservoir from the cells. By that, we confirming that the cells will be protected. They get the anchoring that they need to seed uniformly and to grow without damage with the high shear stress. And by applying perfusion, closed-loop perfusion, we can seed them uniformly on the scaffolds and also supply them with the media they need to do the nutrition transportation and the gas transfer. So here you can see how the scaffold looked like before the processing, and this is how the tissue is being created within 1 week. And this is how the macro tissues look on a pan. And you can appreciate that we're talking about something which is far similar to meat compared to the cell slurry. And the great thing with working in a high solid to liquid ratio, because when moving from the mixer to the columns, we are basically working in a totally different engineering principles that allow us to increase dramatically the amount of scaffolds and consequently the amount of cultivated meat that we can yield from a given column. And in our current pilot system, we can yield more than 70 kilograms out of the total volume of edible packets of 25 liters. It means 68% solid to liquid ratio and product to working volume, which is quite high. So the main element in our system is the edible scaffold. We designed the scaffold to be part of the system, not part of the product. I mean, the flat in terms of flavor contribution. They are protein-free. They are made of plant, edible material, animal component free, high porous material. It means that the weight of the scaffold out of the total mass is only 3 to 4%. It allows a lot of space for the cells to adhere and to create tissues. If we compare to the equivalent surface of 2D to our current system that looks like it's the size of a closet, it will be comparable to 5 basketball grounds of equivalent surface. And it allows us to reach high cell density relatively to scaffold-based cell growth of more than 40 million cells per ml, with a very high cell doublings on the scaffold that allow us to work with lower amount of cells before differentiation, so we can get even 5 to 6 and more than 6 doublings on the scaffold. The scaffolds are very cheap and it's autoclavable. It means that we can sterilize them inside the system, and by that we avoid additional aseptic manipulations that can cause contamination risks. So we confirm that this platform is cell and species agnostic. We confirm that we can grow using this platform fibroblast cells from chicken, from duck, adult stem cells from chicken and from duck, different type of fish, and bovine adult stem cells, and also myoblast. It's not only cell and species agnostic, it's also tissue agnostic. It allows us to create muscle tissue, fat tissue, liver tissue, and of course connective tissue. So in this study, we wanted to understand better the influence or the advantages of growing cells on scaffolds on our platform compared to just growing cells in suspension. We hypothesized that growing cells and give them the natural conditions, and growing natural cells will allow us to yield better nutritional and also organoleptic characterization from the cells. And the first thing that we saw, and it makes sense, that if cells need to grow on scaffolds, they need to invest in structure, right? They need to adhere to something, they need to apply contractile forces, so they produce more protein. So we quantify it, and we saw that from each cell, we get 6 times more protein compared to just growing the cells. And more than that, they need also to maintain their external protein structure, the non-soluble protein, such as collagen, and we get 25 times higher collagen from each individual cell. Eventually, we get more collagen for a given milligram of product. And very interesting that we wanted also to understand the contribution of growing the cells on the scaffold compared to just adding them to the scaffold, because this is apparently what a lot of companies doing. They're taking the cell slurry and adding it to plant-based material in order to impact the organoleptic flavor and smell. And what we figure out is that basically you get more organoleptic contribution from each cell when you grow the cells on the scaffold compared when you just adding it. And it's comparable to almost 50% cells when we're just growing the cells on the scaffold. And this is, by the way, without differentiation. Now moving to the differentiation, which our platform gives a lot of advantages for differentiating fat tissue. You can appreciate here how we're doing differentiation to fat tissue. And this is in the micro level. As you can see, we show that for a given milligram of cell pellet compared to our cultivated meat, we get 68 times more lipids. And it means that each individual cell contributes more than 1,500 times more to lipid accumulation. This is very important for the flavor of the species-related flavor. So here you can see undifferentiated cultivated meat compared to the differentiated, and this resulted in increasing intensity and similarity with the conventional chicken meat. And this study that we've done in a collaboration with Profuse, where we differentiated myoblast, chicken myoblast, within 4 days to muscle. And as you can see here, the differentiation resulted in an increase of 80 times more myosin heavy chain on the scaffold. And as Mark mentioned yesterday about the influence or the impact of differentiation to muscle to the texture, so it is very important. But more than that, the scale is also important. And what you see here is into scale spheroids or microbeads at the same size of 300 microns compared to the macro tissue, the macro structure. And you can see that there is totally different size of the myotubes that you can get. And this is a one-way ticket process. I mean, you cannot fuse them and then get the longer muscle fiber. So we wanted to confirm that this technology can be scalable. So we scale from a few grams that we do in mini bioreactors to the pilot scale where we can produce more than 10 kilograms. And we search for linear scalability, and we got linear scalability in terms of protein concentration and also cell density, and I don't show it here, but also organoleptic characterization, showing non-significant difference between the few grams to the 10 kilograms that we produce using our pilot system. And more than that, we explore the uniformity of the protein distribution and also the cell distribution in the depth of the column and also in the radial region, showing that the protein and cell density are uniformly distributed inside the packed bed. So to sum it up, our technology allowed to yield more from cells, more nutritional level protein, lipids, to utilize better the cells to make an impact on the final product. All of this is also contributes to cost reduction in the media and also in the cost of the system, which are much more compact, and then it reduces the depreciation on the final product. And finally, it's not compromised with the final product. It means that allow to produce structured tissue that can be part of more premium products, and you can do it with natural cells, non-GMO cells. And with that, I would like to take your questions.
Any questions? Yeah. On the left side. Many questions, good.
Thank you for the nice presentation. I have a couple of questions. What is the moisture content in your harvest product? And also just to confirm, I understood that the percentage of weight of the scaffold at the end was 3 to 4%, but I just want to confirm if that's the reality.
Yeah, so the moisture is dependent on the cell type. The best performance was like 88% moisture.
And the percentage of scaffold at the end, that remains?
Scaffold remains the same. As I mentioned, it's something like 3%.
3%, okay. Thank you.
Other questions?
Thank you for your presentation. I was wondering, when you showed results in protein, so you showed that in your system the protein was much more than with just cells. And I wonder what the contribution of that is the scaffold. Yeah, you just mentioned that it was 3% of scaffold compared to cells. But without scaffold, like, do you know if this protein comes from scaffold or cells still?
Yeah, so the result is subtracted. We subtracted the protein. It's negligible amount of protein on the scaffold because there is no protein basically on the scaffold. So we subtracted the scaffold as a blank from the result.
What kind of scaffold is that? They look like lentils to me, but maybe something else.
This is our secret source. I can.
Okay.
But it's. I just will say that we designed the scaffold to allow us to work in a packed bed configuration. So it's not only that it allows us the highest biomass, but also to maintain those physics that allows this flow through porous matrix, and allow the highest biomass that we can.
Okay, thank you.
Thanks for your presentation. So I understand that your volumetric productivity is really high in your packed bed compared to a stirred tank reactor, but you of course also need your bioreactor next to it to oxygenate your medium. What's the ratio in volumes between your bioreactor to oxygenate and your packed bed to grow?
Okay, so you mean in terms of scale up, or?
also in terms of scale up, but if you have one packed bed of, let's say, a few centimeters, how many liters of bioreactor do you need next to it to pump enough oxygen in your medium again to get it through your packed bed?
Okay, so if I understand correct the question, the oxygen is a key issue in scale-up, and in the size. It will basically determine the size of the bioreactor. Currently, we're working on our next scale with our partners. The next scale will be 200 liters. Currently, the pilot is basically composed of 5 chambers of 5 liters each. We're now doing scale-up of 40 times to 200 liters. And we do the scale-up very similar to purification procedures in column. So we created a small scale with the same height. And using the same height, you basically make sure that you have the gradient of the oxygen that you need to supply, but also the flow rate that influence the distribution and the shear stress inside the scale. So maybe next year I will present, but we successfully showed that we can work in the height of the next scale. So I hope that next year I will show you the production scale, not only the pilot scale. So the height will be the limitation of the system, but because the system is modular, so we show that we can run it with 200 liters, and then because the system is very simple, we can do scale out in a very low cost and do the scale up basically using scale out methodology. Okay.
Yeah, thanks.
And another issue is that the reservoir is cell-free. So we use in the reservoir fermenters, not bioreactors, because we can use the maximum KLA exist. Maybe even in the future, just heat and oxygen exchangers.
Due to time, we have to go to the next presentation, but thank you very much again.